I think keeping up with the era of where everything is big, I have a talk with a very big title. So it's probably among many talks I have given, I think this is probably the biggest title I have. What I'm going to do is I'm going to keep up in the spirit of the nature of this summer school, and I'll make some broad brush strokes about the work that I did while being at UC Santa Barbara. And I think if some of you follow me, I've been floating around in the era of cloud computing. I spent some time in Google, and then I went to Qatar. There is a national lab there called Qatar Computing Research Institute, and then I've come back, and I'm somewhere between Google and Santa Barbara. So what I've done is I'm going to give you the glimpses of things that I have done and some of the challenges that arise in the context of the work that we have been doing for the past few years. So that's kind of is the spirit of the talk. And I hope I stay awake. So, if I'm dozing off, please ask questions. Okay, so, the given is that we are really dealing with huge amounts of data. There are, everywhere you go, people talk about data. Data seems to be the new economy, the new currency, new everything. But the fact, from a computer scientist or a systems guy's point of view, the challenge you have is that there is this vast amounts of data in terms of large amount of text documents, large amount of annotated images, and what's happening increasingly and interestingly as we interact with these data-intensive applications, we are creating really a trail of human activity in terms of these log interactions. Okay, and most of you are very, very young, but I have a privilege to be in an age group where many things which I read as a science fiction has now turned into reality. So a lot of the things that we used to think about as being really futuristic and forward-looking is now today's reality. So self-driven automobiles, automated image understanding, and most recently, what people have been talking about is modeling the brain. Okay, so these are all the good things that go with it. What I'm going to give you is the ugly side, in some sense, is what are the challenges and where we are when it comes to making this all happen. So to do that, first of all, let's look at why is everyone happy with this bigness of data? So one of the things that is nice thing in the context of computer science is, somehow at least we have resolved the notion or the model among the people who sort of machine learning folks or data mining folks as well as database folks is that you can model the data as either as a table or a two-dimensional matrix, and it seems to like a nice model. So somebody like me, who's a systems guy, I'm very happy when the number of rows in this table or the number of rows in this matrix increases, many-fold, and that creates a big challenge for me from a scalability point of view, because very simple problem. For example, if you're only doing a duplicate detection in a relational data, it is an n-squared problem in a classical sense, and that's no matter how you do it, it can be just scaled linearly. Okay, so that keeps people like us happy. When it comes to, when you go to the data mining or machine learning side, what happens is they're happy because what's happening is you are increasing the width of the data by introducing more and more attributes. So people are already talking about having billions of attributes in a given data sets. So that gives rise to the statistical hardness, because it gives them an exponential complexity in terms of as to figuring out what are the correlated attributes or how to build the right model. Okay, so that's keeping these communities happy, and they can keep doing their stuff independently. But what my goal in this talk is to bring together these two communities together and try to tell them that if we work together, we can probably do better. Okay, so just to at the outset, when I have often confronted with is what is data analytics, what is data mining, and what is machine learning. And what I'm going to do is just, take a kind of a teaching or pedagogical approach, and let's try to just distinguish the three problems in a very, very simple way. So if you are given a sentence, which I've shown here, and you want to find out, given this sentence, what is a database problem? A database problem would be is counting the number of times Apple appears in this particular text. Okay? The mining problem would be is you're probably interested in the interesting pairs, or sorry, so this is not working.
It should be working.
No, it's not working, I think.
Because you have that? No, it's okay. I don't know.
It's okay. It's all right. I'm close enough.
Maybe the battery there?
No. I think it must be that it is not configured properly.
Off. Huh? Now it's on. So let me see. First, that is working now.
Yeah.
It is working.
Yeah.
Okay.
So just to simplify things, the data mining question would be is what are the most frequent items that appear in this sentence? And then as we go to the higher level, which is the learning problem, you want to be able to understand if the concept of a fruit, which is labeled as an apple, appear in this text. So this is how you can distinguish that. So given, if you think about just looking at the overall picture, what you're dealing with is applications, and the applications are generating, are internalizing the modeling the physical reality, and as a result of that reality, you basically either have observations and application-related data. And that on the right-hand side of your screen, what you see is the traditional and data analysis that we have been doing for the last couple of decades, and significant advances have happened as a result of the largeness of the data. And there has been, the data mining issue is to doing clustering and frequent pairs and pattern recognition. And the learning is the eventual goal is to model the reality based on the observations you have. So what I'm going to focus on this part and this part in the next few minutes. Okay, so let's look at the data management problem, and the change that has happened in the last 5 years is there has been a tremendous paradigm shift, and basically what has happened is essentially most of the applications that we interact with today has all moved into what is referred to as a cloud. Okay, so the question, I think, one of the things is we can ask is why has that happened, and I think I can go over it, but I'll just reiterate, and the reason is that in the last decade or so, the data center as a technology has proved itself. That basically it gives you significant economies of scale. It actually, from a usage point of view, it does transfer of risk from an individual user to an aggregate provider, where you can basically aggregate the risk over many users, and that becomes substantially better. From a technology point of view, is that there is one of the things that has happened is there is availability of broadband internet has made things very, very different. Right? And the second thing, which not many people talk about it, is but there has been also that this whole thing has been enabled because of the virtualization. And finally, I think since I heard a little bit that there is an entrepreneurial bent to this summer school, and one of the things that you have to always remember, that technology alone, no matter how good your technology is, it's not enough for an inflection point to happen. It basically has to align with the business factors, and that, I think, is why the cloud computing has been successful. So the promise of the cloud is that if you're basically in the past, in the classical sense, what you had to do was you had to do the capacity planning in terms of what your peak usage would be. Okay, so you try to figure out or model your demand curve in what was going to happen for given the service you're deploying or an application that you're going to launch, and based on that you have to plan judiciously as to what your capacity should be. The promise of the cloud is that you really don't have to worry about it. You don't have to create any infrastructure. What you're going to be given is you will be provisioned automatically that, as your demand shifts, we are going to provision the resources as. Now, this is very easy to say, but it is very difficult to design applications and design systems that can hug along the curve as your demand shifts. Okay, that's, I think, is one of the things I want you guys to understand. So just to take this a little bit further, I think given that you have the cloud and sort of provisioning of resources on demand, as you increase your as a service deployment becomes popular and you increase your client base, you can very easily scale the middle tier components. Okay, the problem that arises and that has been experienced very early on was that data becomes the bottleneck in this architecture, and that's, I think, has been recognized very, very widely. And what happened with that is that people went away from the databases, which was a proven enterprise technology for more than 2 decades, and instead decided to use these homegrown systems, which are referred to as key value stores. Now, what they gave up in terms of using these key value stores was essentially all the goodness that came with the database platform, the issue of atomicity, the issue of consistency of your data, the issue of failure resilience and recoverability of the data, all that was thrown away, and instead you have provided this. Now, it's not that people don't need these good features. What is happening, and this is, I'm sort of giving you an inside view, what has happened is, in effect, the onus of building all those properties now shifts into the application layer. So the applications now have to do all those good things, and they have to figure out ways to get around this problem. Okay? Now, so if you're building one application, yes, you can do it. But what happens is now when you have in a large entity, pick any internet company which has a large number of app products. Essentially, effectively, what starts happening is every engineering team start duplicating the efforts in order to build these things. Okay, so this is not a tenable solution that has been recognized at least by some of the industry leaders. I can't go into the specific, but some of the industry leaders have recognized that this is a problem, and they're kind of coming back full circle to rectify that. Okay, so the approaches of scalability, the classical approach of scalability in the database context was essentially when you want to scale, you buy bigger machine, and that's how you scale. What happened in the cloud computing model is because you're dealing with key value stores where each entity is independent, essentially what you can do is you can take your data, which is sort of loosely related, and you can break it apart into many pieces. That's essentially what key value stores do. And as a result, what you do is you are able to achieve significant scalability. So that's kind of where we were about 4 or 5 years ago. And I'm going to skip this, but essentially, I don't want to dismiss the key value stores as being not very useful because I'm a database guy. What comes out is there are certain design principles which you can learn from and try to use that as a feedback into the database technology that you're going to build for the cloud. So that's kind of what you can learn from. So one of the things that comes out is when you're dealing with database type of applications in the context of the cloud, there is this notion of a system data and the application data, and you want to decouple that. And the system data has to do with as to how your applications are using multiple resources and what kind of mappings you have and things like that. And you want to maintain that very, very coherently and consistently. The other thing what happens is, even though in the context of the cloud, you're using many machines, as far as the user interactions are concerned, you want to isolate the user interaction to a single machine. Okay, so that's what Peter talked about. This is the latency sensitivity that comes into play. If you start doing a very, very complex distributed transaction using many machines, for us, every user interactions, it's not going to go very well. Okay, the third thing that comes out, I'm going to go into a bit more detail, is that you want to sort of decouple the notion of ownership of data from the data storage itself. And the reason is, you want the ownership to kind of float around depending upon failures and kind of automatic scaling and things like that, but you don't want that to be coupled with data movement. And finally, that if need be, some amount of distributed synchronization is okay. Okay, so how do we go about building scalable databases in the cloud? Well, we have two endpoints if you think about it. So one is the traditional databases, and what you can do is you basically take the traditional databases where the philosophy is that you treat data as a whole and try to figure out if you can break it into smaller pieces. And that is what has been done in the past few years in multiple systems, both in academic settings as well as commercially. So in particular, for example, Google's F1, which is used widely inside Google, basically uses that technique. The other approach is you start from key value stores as your building block and try to infuse some of the database principles in that context, and I refer to that as fusion. So you bring keys together and try to treat them into coarser, granular atomic entities. So there are, once again, there are pieces of work that exist in that context, and so the G-Store is from my group, and Megastore is from Google, where they basically designed a system where entities were grouped together to fuse the multiple keys as a more coarser notion. So the basic idea about this is the basic building block is really to partition the data. And the partitioning of the data has been around, the table partitioning idea has been around in databases for a long time. So what is different? So the difference is that I think you have to do a more careful or more semantically richer partitioning, where you try to take into account the schema information itself to break the data apart. Because if you just do kind of a simple table partitioning where you just throw the tables and break the tables into pieces and store them on multiple machines, what can happen is many of your interactions, so user interactions, will end up having distributed synchronization problem. So this is basically was the idea of the work that we did in Illustras, and SQL Azure from Microsoft and F1. They all have the similar idea. So you basically do your data partitioning into the smallest granule based on your schema structure. And this obviously it does not provide, it does not deal with all possible schemas, but if you especially have tree structured schema, which is very often the case, then you can do this very, very easily. Relatively easily, I shouldn't say that. Yeah. There has been also, from Sam Madden's group at MIT, they have also looked at this issue from a different point of view. They basically did the workload-aware partitioning, and the idea was you learn from the workload, and based on that, you break the data apart so that there is minimal sort of synchronization across these partitions. Okay, so I'm going to. So with that, I think you can, once you accept this idea, then you can go about building an architecture which will be much more cloud friendly and which will allow you to do database-like activities in the context of cloud. So essentially, what you have is so the most important thing is this metadata manager, which basically maintains the system level information where it maintains what the mappings are. Is there a question? Okay, and you have these transaction manager which are managing some subset of the partitions. So essentially, if you look deep down inside, there is a master which maintains the mapping of partitions to the transaction manager, and essentially this gives you enough, if a particular transaction manager becomes overwhelmed because of the workload, you can take those partitions and you can split across many, and similarly you can group them together. So that's basically the idea. And the assumption here is at least in the data center setting that your storage layer is independent from your execution layer, which I'll come to again later part of my talk. Okay, so in the context of data fusion, the idea is essentially you want to be able to do is you have these keys around, and the problem is the read, modify, write that you can do is only at the single key level, but there are many applications which want to be able to perform these application interactions on a group of keys in a transactional manner. So Megastore, what it did was it basically allowed you to statically group the keys together so that they are allocated on a single machine, and that's how they manage the atomicity of these multiple keys, the transactional access to these multiple keys. In the GStore mechanism, the system that I referred to, what we did was basically we allowed the dynamic grouping of the keys, and the idea was that if these keys could be scattered on multiple machines, what you do is because you have decoupled the ownership and the data storage, what you can do is you can bring the ownership of these keys to a single machine in a dynamic manner, and then you can treat that as an atomic entity for the time of the duration of the access, and basically once that is done, then you can disband the group. So that's basically the conceptual idea. Okay. I am going to, so this is essentially this was what I did was talked about this, how do you scale database technology in the context of cloud. Now another thing that comes in the context of the cloud is that you also want to make your underlying platform or underlying database technology to what is referred to as being elastic, which is being able to scale it on fewer machines to many machines and many machines to fewer machines, depending upon your workload. So what this means is that you have to be able to do what is referred to as database migration. Okay, so you without interrupting, so without without bringing down everything, you want to do on the fly live migration of databases from one machine to the other. Okay, so the idea of live migration has been around for some time. So for example, in the context of virtual machine, there have been several proposals for doing the VM migration in a live manner. The difference is, I think, when we are dealing with the databases, is that you have the storage component associated with it, and that I think becomes an issue. So I'm going to skip over that part.
You have until
I have an hour, but I want to spend. So I'm going to flip through the slides. These are, So this is, So the idea of elasticity is essentially it comes in the context of, you take a multi-tenancy type of an application where you are a database provider and you are hosting multiple database users on your system. And as a provider, what you would like to do is you want to use minimal resources because you want to maximize your profit. So you want to start out with as few resources as needed in order to satisfy your customers reasonably well. But when the number of customers or number of the workload increases, what you don't want to do is you don't want to upset these people. So you want to be able to satisfy them by scaling them out onto more machines. So that's kind of is the idea. And similarly, when things become, there are fewer users, the workload reduces, you want to consolidate. That's kind of is what you want to be able to do. By the way, this is not only for, I gave you an example of a database provider, but you can pick, Google or Amazon or Yahoo. They all want to be able to do that because they are all realizing that, as the footprints of these applications become large, there is a cost associated with using these infrastructures. So this whole idea, this model, is being recognized as an important model. So, so the idea is, I think the data migration actually depends upon the database model that you're using. There is something called the shared disk model, and there is a shared nothing model. So if it is a shared disk model, then it is a relatively simple. The migration itself is relatively simple. What you have is you have the database state and the transaction state, and you want to move this. So you want to move this state to another place. So you have to basically figure out, I'm not going to go into the details, but you have to figure out a way in a safe manner to be able to migrate this memory state from the cache and from the transaction state and move it to to another site and switch your users, the live users, from one machine to the other. And the challenge, the technical challenge is, how do you do that in a safe manner, right? Without aborting transactions and without disrupting the whole thing. So that's kind of is the idea. So I'm sketching out the problem formulation. I'm not going to go into the details of the solution. So this is some performance numbers, which is, I'm not. In the shared nothing architecture, things become a little bit more complicated, and one of the papers that we had is we basically had a solution where all accesses happen through an access method, like a B tree or something like that. If you take that, if you're given that environment, then what you can do is you can basically take the access structure, you freeze it. Essentially, don't allow anything happening on the left-hand side, and you copy the access method, and then as activities happen, you populate your databases. Okay. Although this is a solution that exists, I think in the cloud computing model, just this whole idea of moving data from one place to the other is not a tenable solution. So that I'm going to come to that in the latter part of my talk. Okay, this is where I want to move. So let's talk about learning, okay? And I'm going to. So I'm not a machine learning person, but I think what I did was I spent a year at QCRI, and one of the nice things in QCRI was I was able to interact with people from multiple disciplines. And I think during that, I think I got some education and a basic understanding, I would say a freshman level understanding of what machine learning is. So if there is ML people, I don't want them to be offended. I'm really not standing here as an expert, but I'm more standing here as a student here. So what I understand is the following. Is, from a machine learning point of view, when we talk about application and collecting information, sort of observational information related to the application, like your Facebook interactions and anything you do on a shopping site and things like that, from their point of view, these are really examples or observation of what the real model is. Okay? So the holy grail of machine learning is to be able to find a model so that you can explain user behaviors, for example. Okay, so that's what. And here is a sort of one slide summary of what you would want to be able to do. So given that you have, and in this case I have taken two-dimensional sort of observations in the two-dimensional space. So here are your observations, which is the xi's and xj's are the represents sort of the elements. The user was UCSB professor, lives in Southern California, and so on, all those things. And the YI is a label associated with this. So whether I buy something or not buy something. So that's a positive. And so we are just looking at the binary result. So given this distribution, what you want to be able to do, so you now have to think about, even though I'm showing you on a two-dimensional surface, this is obviously, these are multidimensional features, okay? So in this multidimensional feature space, what you want to be able to do is find a surface or find a line in the context of a two-dimensional where you can explain the positive or negative behavior or separate the positive or negative behavior with respect to that model, okay? And generally, I think, given our constraints, these surfaces are linear. Right? Essentially, you build linear models, because anything beyond linear models becomes much too complicated, and I don't think we have reached to the level where we can deal with nonlinear models. Okay. Now, given that we are restricting ourselves to linear model, what's going to happen is you are going to have some errors, right? So you draw the line, and something which should have been positive is negative, and something that has been negative, which is positive. So it's in the wrong side of the line. So what that means is that you want to figure out your hypothesis, and with respect to the hypothesis, you want to measure the error that has happened. And there are some clever tricks with regard to what is referred to as regularization. For the purpose of this talk, let's not worry about it. It just has to do with picking the line which is the nicest one in some sense. Okay, and that's kind of is a mathematical formulation. Okay, so this is what the learning, the ML folks will do. Now the really exciting thing comes in is that you want to do all this in a big data setting, and what you want to be able to do this is when you have feature space which is of the order of billion features. Okay, so there are people are talking about building models over feature sets that are that large. So these are columns, the number of columns going over a billion. Okay, so the question is, how do you do this when you have large amount of data? Okay, so you have large number of observations, which could be easily in the 10 raised to in the trillion, and it is very wide. Okay, so just to formalize, the model is you formulate your hypothesis function. Based on that hypothesis function, you formulate your the loss function or the error space. So what you want to do is you want to minimize the cost. Okay, and the typical solution for minimizing the cost is often this function is fairly, it's not differentiable. If it was differentiable, you could easily do it mathematically and be done with it. So you end up using these techniques from linear algebra, which is basically based on some iterative functions, and these are based on what is referred to as a gradient descent. Okay, so this is where kind of our interesting things happen from a systems point of view. So now I will take that and I'll convert this program into an iterative program, which is what I understand. And essentially what you're doing is that you're reading the parameter space or the feature space, you're computing the gradient, and then you are writing back the next sort of the values for the next iteration, and then you just iterate over it. So this is what the function is. Now, the problem is that given the size of the feature space and the amount of data that you have to do in order to compute the gradient, you want to be able to do this in parallel and distributed manner. Okay, so you can actually do, you can look at, there are two aspects of data here. One is is the number of rows in the matrix. So you go back to my matrix and look at the number of rows. That itself, I said, is already in the trillion range. And the other one is the number of columns, which is the feature, which is of the order of billion. So what I'm going to do is I'm going to focus on the feature partitioning just for this discussion. And what we are going to do is we are going to partition the feature space into multiple sort of disjoint parts. Okay? And the idea would be is by partitioning these feature space, I can compute this feature space in parallel, and that's how I'll be able to expedite my processing. Okay, is that clear to everyone as to where I'm going? Okay, so here what we have is I took my feature space and I created D partitions over it. And now instead of reading that billion variables, my problem is to read these partitions, compute the gradient, and each of these parallel thread or worker is responsible for one partition. Okay? So unfortunate part is that you cannot completely parallelize the computation. There is a dependency, that is, you have to read all these features before you can compute the gradient. So you have to read all the partitions, even though you are only manipulating, writing, or modifying, or updating a single partition. Okay? Is the dependency clear? Okay, so what happens is, essentially, since you are doing this iteratively, you can immediately see that there is a synchronization issue that comes into play, is that when I'm trying to read all the partition, I have to make sure that everybody else has finished up to a certain stage before the values are available for the next iteration. So as I'm doing iteration, each iteration I have to make sure, so there is some amount of read synchronization. Similarly, there is a write synchronization, which tells me that I can't go and write something, because if there might be somebody who has not read the value that I had created in the previous iteration. Is that clear to everyone? Okay. So the classical technique is what is referred to as process-centric synchronization. I mean, most ML papers that you pick, what they do is they use this notion of BSP, or bulk synchronous parallel, where essentially they use the analog of our mutual exclusion operating systems principle, where they basically create barriers. Okay, so the barrier, if you formulate it as a formal condition, essentially what the barrier is saying is that before I can perform my read, I have to make sure everybody has finished their writes of the previous thing, because until they have finished that, I know that the reads are not ready for me. Okay, I cannot read. The data is not available to me. Similarly, when I come here, I have to make sure that all the readers have finished their reads in this current iteration before I can write. That's what these condition is saying. Now, obviously, if you have this level of synchronization, then your hope of making this faster is not very. It doesn't work, because essentially what happens in this context is the amount of speed up or parallelism you get is blocked by the slowest computer or slowest worker in your computation. So you could have thousands of workers, but if there is one slow worker, then you're stuck. Okay, everybody is going to go with the speed of that worker. Okay, so the question is, how do we do it better? Okay, so what is happening in the ML arena is the approach that is being taken is what is referred to as a function-centric approach. Okay, so what a lot of the scalable ML algorithms, what they do is they focus on the function that they are trying to optimize, and they look at the semantics of the function to reduce the amount of synchronization that is necessary. So there are, if you pick up any paper in the last few years on this topic, you'll find that they have an ML abstraction, their formulation, but then they will start talking about at the level of the memory operations, the read operation and the write operation, and the race condition and the write. That's where things are. Okay, and then they have an extensive proof to show how the properties of their function can be guaranteed in spite of these synchronization violations. Okay, so this is where the things. So those are few. If you think about it, is the question I started asking: why do the ML folks have to reason about low-level details at the machine level? Okay, in the same way that we could provide the transaction abstraction or atomicity abstraction at the database level, where any application can be built on top of it, why can't we do something similar? So that's from an academic point of view, or from a research point of view, that's a good question to ask. Okay, so that basically what I'm saying is, why can't we move from a process-based synchronization to the data-centric synchronization or data-centric approach, which is what we use in the databases. And it turns out, and you have to take my word for it, is that if you sit down and start thinking about, can I use a database system which provides me two-phase locking, transaction abstraction, can I implement this iterative process that I just talked about on top of the database? And it turns out the answer is no. Okay, and just take my word for it. If you want, we can talk about it. So if you are able to do that, then you can do overlapping, because then what you do is you really don't have to wait for all the reads to happen or all the writes to happen. You can start doing look-ahead computation and really wait whether wait is absolutely necessary at the data element level. And it turns out you can take those conditions and you can transform those conditions to stipulate them as follows. And this really significantly weakens the requirement. And here what it says is that if I'm worker I and I'm reading a partition J, I don't have to wait for everybody else. I only have to wait for the writer who's producing the partition J. Okay? And similarly, if I am the writer who's producing J, I only have to wait for everybody else to have read the partition J. I don't have to worry about whether they have read other partitions or not. If they have read my partition, then I can go ahead and do the computation. Okay?
But isn't it like, because you do summation when you do gradient descent?
Yeah.
So you are dependent on doing the aggregation step, no?
Yes.
Which means that everybody's writing, huh?
Everybody's right. But you still can, you still can get the overlap in terms of doing the receiving and communication overlap. So with that, the initial evaluation, we are able to show that we can do much better scaling compared to the bulk synchronous approaches, and with some number of iteration, you can get significant improvements. So 60-70% improvement over the BSP approaches. So what I gave you is really a picture of doing the feature partition. But in full generality, what you want to be able to do is you want to also deal with the data partitioning, and really you want to be able to go there. So I don't think I have answers to that, but this is what sort of the assignment looks like. Essentially, what happens is you want to have a characterization of what sequentially consistent execution mean in the context of iterative computations. Okay, it's something similar to the serializability in databases, something similar that you need to come up with that characterization. And then with that characterization, you can look at a data-centric approach and you can look at the process-centric approach and make sure that these approaches guarantee sequential consistency. Now, the interesting thing is once you have this formulation, you can obviously, on top of it, you can also always add the notion of function semantics to be able to do better. Okay, so this is where, I think an interesting area for work.
And you might even have a hierarchy that could be weaker sometimes.
Weaker assumption. So you can, for example, you can do bounded delay type of computation. So you can allow the workers to, or if the change in the values is not significant, then you can skip that. I mean, I think given the nature of ML, you don't have to be completely synchronized in some sense.
So just maybe a comment for the students on that, because when I was giving the talk, I was talking about this optimistic fault tolerance, which essentially is a dual problem, because there you also exploit the fact that you don't have to be fully consistent when you lose data. It's in a different application, but it's dual in a sense.
Yeah.
Which has to be
But the point is that when you do these loosely synchronous stochastic gradient descent, the learning process itself will become much slower. So it takes time to do stochastic linear gradient descent, for example, compared to the normal gradient descent. So I think we have also to see what is.
That's an interesting point. Right. So that's true. So you could have a less synchronization, but you might take longer to converge. The convergence might be slower. But it is, nevertheless, I think it's an interesting interplay. Yeah. Yes.
What about then, since you have knowledge with what Google's doing, like with their automated vehicles and that
I can only tell you about the Google's the 2012 NLP paper, and if you want to ask me questions about that, I can tell you. But otherwise, about the vehicles, I first of all, I don't know, because I'm far removed from that, and even if I knew, I think I wouldn't be able to tell. But basically, I think so this is the paper with Jeff Dean. This was in a NIPS conference in 2012. This is about deep learning, and this is essentially the multiple stages of neural network. And the idea they have is the same, is that we essentially, if you try to do tight synchronization, it's too slow, so we allow things to happen kind of in a loose manner. And there is a statement in the paper which explicitly says that, we don't have any theoretical we don't have theoretical formulation as to why this works, but nevertheless it works in practice, and that's good enough. I think that's how it ends.
I just want to say to the students, tomorrow we'll have a lot of machine learning sessions. So you can ask the student.
Yeah, so it's really a fascinating, I think, interaction with the machine learning folks. I think that's something really for us to learn from.
That was just that. This is the opposite kind of problem where you have to do things in real time, detect objects and these kind of things that do this kind of techniques apply there, or is it something completely different?
Yes. Once you create the model works in real time. Because you have to create. This is the learning process.
Yeah. So this is sort of the offline process. That's right. Okay. So what I'm going to do is in the 10 minutes I have, I'm going to give you a little bit of. So I've been. I spent not last year, a year before. I spent a year embedded in a product group, which is called the Advertising Data Infrastructure, working with them, and I really was working at the level of a junior engineer. So I essentially wanted to understand and these technologies and what are the challenges and things like that. So it has been a very fulfilling experience. And from there, obviously, I have formulated some of my own ideas, and what I'm presenting here are really my thoughts on where are the challenges and what we need to do. So the things that I've picked up is this notion of data centers. How should we view a data center, and how should we be designing applications and systems for that? The second thing is what is increasingly happening is really there is, we talk about, for a long time, I only think about a database as being a single entity. But in reality, what happens is the data has to move through multiple stages, and these are called data pipelines. And actually, there is a talk today in the later half of on something called Cloudflow, Google Cloudflow, which is exactly trying to address the problem. Is that in the context of large amounts of data, when multiple sources of data becomes available, then you have to create these data pipelines, and that really is becoming a challenge now. Okay, and then finally, I think this is more to, I think, is the issue of what in Google they are referred to as multi-homing. In the outside world, in academia, it's called geo-replication, and I'm going to motivate this from a different point of view, I think. Okay, so let me just give you a little bit of a story about this company called Dropbox. Okay, so I don't know how many of you are familiar with that, but I will tell you the evolutionary story which I kind of have understood. So Dropbox, as it is true with many successful companies, it started out in a dorm room. Okay, so if you guys are still a student, you have a chance to become a billionaire. Otherwise, it's too late. They basically started with when they started out, they had a single machine, and which was a managed machine, their own machine, and they were using the cloud primarily as a gateway so that the users could access their machine. So they were running a server, if I may. Okay, they pretty soon realized that that's not a tenable solution. So what they did was, the next step, what they did was essentially separated the computation from the data. So they had dedicated machine for their data, managing the data, and a dedicated machine for doing the computations. And the data also, they separated into two parts. They separated the data into the file level data, that is the content of the files. So as you know, Dropbox is basically a file management system, right? And then there is a metadata which is about the files and locations and the ownership. So that was managed, and that was a critical data, because that's, I think, is maintained, told them everything about the current state of the system. And that they used a MySQL type of a database technology to manage that data. And the file level content data, they basically offloaded it to Amazon S3. Okay? And then I think the next logical step was they realized that their single server was getting loaded, and so they separated out the computation into three different parts. Logically, so something that was serving the file data, something that was serving the file metadata, and some sort of notification server. So this is how they separated out. Okay, so this is, so they basically went very rapidly from a single machine to this multiple machine architecture. They did it relatively quickly. The interesting thing was, then as they had to scale their service with the demand that was surging, they had to go to multi-machine architecture for each of their components. And they did it, but the problem was that it took them about 4 years to go from here to here. And this is, by the way, this is based on the presentation that one of the Dropbox engineer gave. So all I'm doing is I'm regurgitating that story. So the question, I think, we as academics or researchers and students, you guys have to start thinking about is, why does it take us so long to start from a sort of a multi-server architecture? Why does it take to move these infrastructure to a parallel and distributed environment? And what are the missing elements when we are designing these things? So this is something that I don't think there are solutions there, but we really have to figure out if we want to stay in the cloud arena. So, and I think my thinking is that the reason is because we are used to the old way of thinking about machine as a single element. I think you have to start thinking about a new computing substrate, new storage substrate, which is this data center. Okay? And what happens in the data center environment is there is a disaggregation and virtualization of resources. Okay, so basically now you want to be able to look at these processing elements and storage elements as sort of utility components, and you should be designing systems which really views these components in that manner. Okay, so here is where I think I make a comparison between the grid computing and the cloud computing model. This is one of the so there are two things that distinguish the grid computing and the cloud computing is the virtualization. And the second thing is, in grid computing, you still took the classical model of a machine as being a wholesome entity, and that was the first-class entity. And in the cloud computing model, that is no longer true. Okay? So from a database point of view, I don't know. I think the Mike Stonebraker, who won the Turing Award, he has gone on record as saying that he believes the only model he believes is in the shared nothing model, which is CPU and the data and the computation should be together. And I have to disagree with him that in the cloud computing arena, that is not a tenable model. And the reason I'll give you are the following. So the classical shared nothing model, which puts the CPU and the disk together, has this problem with the scaling out and scaling in issue, where if you want to scale out your queries from 10 machines to 100 machines, you can't take your data and move it around. Okay, so that's one reason, and the other reason is the fault tolerance. I think if something, if your machine containing the database fails in the cloud computing, I mean, the whole idea of the cloud is that the failure doesn't matter because you always have something else to go on to, and if you make this thing together, then the problem is how do you go and use the available resources. So there is this necessity of disaggregating the storage from the computation. So that's kind of one way of thinking about it. So once you accept that, then kind of the conceptual model in which you will go about building a database technology or some other application would be the following, is that you basically maintain a storage layer, and you want to make your storage layer fault tolerant and everything, right? And you have a DBMS controller, which is going to kind of orchestrate the database activity or database execution by allowing multiple servers to be instantiated depending upon the workloads. And each DBMS server itself should be able to have enough kind of flexibility to be able to instantiate workable pools based on their workload characteristics. So if there is a query, if there is a query plan which requires you to execute a query on 10 machines, then it should be able to do that. So that's kind of where we should be going towards. Yes, Saif.
So, but again, you have to build the distributed storage layer.
Yeah, you have to build a distributed storage layer.
And the distributed storage layer, even if you view it as a one entity, itself is consisting of components. And maybe these components are even distributed.
Yeah, so at the distributed storage layer, you have to deal with the fault tolerance issues, your replication, and all that. But essentially, but everything. Yes. Exactly.
So you're just pushing the migration to a different level.
No, but I think the migration, I don't think migration should be there, but I think you have to have enough redundancy at the level that you would have some guarantee as to, or some guarantee.
Replication.
Yes. So there has to be redundancy so that there is availability of your data.
It's a lot of movement.
Yeah.
A lot of network.
Yeah. But I think there's no way around it. Like what did Todd Walter from Charlotte said very nicely, I think, what is data is as elastic as a brick wall. Yeah.
So, and I think projecting forward, I think what I think is going to happen is even the memory that exists in this data center is going to become disaggregated. So you will have a shared memory, which is going to be back again. This is my projection. So there are there are issues. There is a network and I/O latency mitigation. I think that's the way you have to deal with it, is batching and pipelining of data accesses. There is a significant challenge in terms of query execution. Now you have the flexibility of, there is another level of freedom when you decide on a optimization plan, how many machines to use. And just using more machines does not make the queries run faster. Believe me, take it for, it doesn't happen. It can slow your queries significantly down if you use more machines sometimes. So this remains a challenge. I'm not an expert in that. And finally, the data replication is whether you do it at database level or at block level. My personal choice would be, I'm a database guy, but I'm not a chauvinistic database guy. I think there are good ideas comes from the systems arena, and I think the file systems people have done that block level replication, and that's a much better solution. Okay, so I'm sorry, I'm going to speed up. So the next thing is, as I said, if you look at the internet advertising platform, it looks a complicated thing. But basically, what happens is you have a database where you maintain the advertiser and publisher information, your clients, and what you do is from a company like Google point of view, whenever there are queries and ad clicks, you log them, and then from there you pull up all that information and try to push it into the database so that you can charge your advertisers and pay your publishers and charge your advertisers. So there is a lot of processing that has to happen in terms of picking up the ad clicks, figuring out the corresponding query, and all that. So if you really peep inside, it really looks like I'm obviously sensationalizing this, but this is how the structure looks. It's plumbing, and now you have to remember. So this is just like in the context of one product. So if you have a company like Google or Yahoo or Amazon, which have multiple products, each product will have something like this plumbing, trying to pull the data from the logs and pushing it into your database. Now, if you think about it, an ad click, from a business point of view, even though it's a very small amount of money, it is a transaction. And the question is, why can't database technology be built so that this can be internalized exactly as a banking transaction that you do it today? Okay, and the answer is basically we don't have the right solution, but I think this would be something that we would want to go to. But in general, I think the general problem of trying to set up these pipelines in a quick and robust manner is really a big challenge. Okay, so I'm not going to let me not say much, but basically I'm going to say is that geo-replication or multi-homing. There are a lot of my colleagues, database colleagues, senior database colleagues who would argue that, the geo-replication and multi-homing is only important for a handful of companies. The rest of the world doesn't need it. But believe me, I think it is an important problem. I think, as soon as you have a deployed service in the internet, so you take the Ubers, something which may become the Uber from 5 years from now, they all are going to need it. And the problem is obviously you're worried about the data, but more importantly, it's from an operational point of view, this is what happens when you're running these 24/7 services, okay? If your provider says that there is something wrong with my data center, you have to take and even if they give you a month's notice, taking your entire infrastructure and moving it from one place to the other is a big undertaking. You have these services which are running on thousands of machines. They have like active state. Trying to move it in runtime from one data center to the other is a significant challenge. Just to provision this automatic failover, you have to be able to do geo-replication, or what is referred to as multi-homing. And internally in Google, what has happened is this multi-homing came about not because they were worried about the data, but because of these operational reasons. They were periodically finding it that when they have to move things transition over from one data center to the other, invariably it was a very, very labor intensive and prone to making a small error could blow up in their faces. And as a result, what they have done is, essentially they have used a cross data center replication layer in many of their infrastructures, and that is based on the spanner technology. I'm going to stop here, and I'm going to get to my... So I'm just going to wrap up. So essentially what I'm saying is that in the cloud computing arena, the three aspects that you have to think about is scalability, reliability, and elasticity. And given that we are living in a data-centric environment, you have to figure out how to re-architect the database technology. Big data analytics and learning, I think scalability, just having the right framework to be able to do scalable analysis of data is a big challenge. And from a big data pragmatics point of view, I think that complex data processing pipelines remains an open era. So for example, today the talk that you're going to hear on Google Data Flow is essentially is a single day data center solution. If you want to extend it to a multi-data center solution or multi-home solution, it's a significant challenge. And that's, I think, is where we are. I'm sorry to have taken time.
No problem.
So
Thank you very much. We might take one question from the professor if you want, and then... Otherwise, then let's thank again.
Thank you very much.